With new technology. Our first speaker of the afternoon session is Amit Chakrabarti from Dartmouth.
Yeah, thank you, Samson. Thank you for inviting me. It's lovely to see this place. It's really beautiful space. Good to meet many of you, and I hope to have interesting discussions with you later on. Well, I think I have a lot to learn from you guys. What I can teach you guys, or maybe tell you a little something about, is hopefully a little bit of a different direction from what you've heard so far. I'm going to talk about lower bounds a bit. Okay. Okay. So we'll start with a recap of something that you understand very well now. Now we've heard at least 3 talks speak about it. An adversarially robust streaming algorithm is, long story short, a streaming algorithm where the catch is that future inputs may depend on past outputs, right? And I think this particular example even was given in one of the earlier talks, where imagine that you're analyzing some viewership trends for streaming video, TV shows, movies, whatever, and you have a recommendation system that recommends what to watch. Based on these recommendations, of course, people choose the next videos to watch, and then this therefore affects future inputs to this recommendation system. Okay, so this sets up a kind of feedback loop, which is what the central challenge is. Now, in adversarially robust streaming, so far there was no adversary. Why is there an adversary? So my take on this is that the world is unpredictable. So we make a worst case assumption here and assume that it could be adversarial and of course adaptive. And therefore, we would like to see what we can do for algorithms, assuming that the world is in fact adversarial, even though it may not be. This is just kind of a safe assumption to make. Now, in classical streaming, you still have a notion of an adversary, but they're not adaptive. They look at your algorithm's code and they come up with some kind of worst case input, which they produce offline. And so the nature of the guarantee that your algorithm gives is point to this. For every input, the probability that your algorithm works well, taken over its internal randomness, is something high, right? 1 minus, maybe I should have called it 1 minus delta. Okay, good. But in the, wrong computer. I shouldn't even need to touch a keyboard. In the adaptive adversary setting, we have, as was earlier mentioned, a game between an adversary and ourselves, the algorithm, which kind of looks like this. So our powerful adversary is generating input tokens. So a token is just one piece of input in a stream. Each time it sees a token, the algorithm, based on all the tokens it's seen so far, computes some kind of a summary of the stream so far, which I'm calling sketch here. Don't think of this as linear sketch. This is just sketch in the general sense. And each time it possibly reports some results or some kind of output to the adversary, who then uses this knowledge to come up with especially hard inputs to give to the algorithm in the future. Okay, so now the goal is a little bit different. We're saying for all adversaries, so meaning for all possible interaction like this, the probability of some error during our lifetime should be at most delta. And at the same time, of course, we want to run in small space. Okay, the algorithm runs in small space. Okay, so why exactly is such an adversary powerful? Where is the adversary getting its power from? So through this interaction, the adversary could learn the algorithm's internal randomness, or at least learn some information about the internal randomness. And this then can be used to generate hard inputs that correlate in a bad way with this internal randomness. Okay, so one way to ensure that an algorithm is going to be adversarially robust is to say, well, how about we don't use randomness? Just design a deterministic streaming algorithm. Then it is guaranteed to be adversarially robust because you've taken away from the adversary this central power, right? The adversary can now, of course, predict everything that your algorithm will do. So he gains nothing out of interacting with the algorithm. Okay, now this, I want to say, is a very stupid method of ensuring adversarial robustness, mainly because restricting yourself to determinism means that you lose pretty much all of the power, much of the power of streaming algorithms, which comes from randomness. We know from classic results in streaming that determinism could be exponentially more costly than randomization. And I like to say, this is like saying, you can't handcuff me since I've cut off my hands. That's a very stupid way to prevent yourself from being handcuffed. Okay, so we do want randomized algorithms, but this makes us think, suppose randomness was being used in some kind of a limited way, right? And as the talk proceeds, we will get more precise about what I mean by limited way. But for example, the algorithm could be what is called pseudo-deterministic, which means that while it's randomized, its output behavior looks deterministic. And I'll be a little more precise about what this means later in the talk, but that's roughly what it means. Well, pseudo-determinism also takes the power away from the adversary for the same reason. The adversary can learn nothing out of the interaction. But your algorithm now has a little bit of power. It actually can use randomness. So maybe it can do something better. So largely in this talk, we'll be concerned with what kinds of trade-offs are possible, and we'll look for more fine-grained trade-offs between exactly what form of randomness the algorithm uses and then how much space cost it incurs in order to be robust. Okay, so I have to talk about these forms of randomness, and that's what the next few slides are going to build up to. So let's return to a couple of classic results from streaming. These are not adversarially robust, these are old results from the 20th century. All right. And I think they already got mentioned in one of the earlier talks, but still, let me rehash. First is the problem of estimating the L2 norm, for which, yeah, I think Henri basically told us more about the algorithm than what I'm saying here. The way to estimate the L2 norm of a vector X that's being updated in a turnstile string is to say you have a sketch matrix that is a collection of random signs, plus minus 1, and maintain S times X, and maintain just the 2 norm of S times X. This is enough. Okay, so we can estimate the 2 norm of X from the 2 norm of the sketch vector S times X. Okay, and the dimension need only be about log n, and this will suffice for good quality approximation. Similar results can be given for other norms. For example, for the L1 norm, Indic's classic result tells us that you do basically the same algorithm, but change S to a matrix whose entries are IID Cauchy rather than IID plus minus 1. Okay, now these are algorithms that use logarithmic space. However, you will notice that they're using randomness in a very strong way. Namely, this matrix S, this matrix S over here is this big random object that they need to use. Crucially, this is central to the algorithm. And what about storing this S? We can't afford to store S. It's even bigger than the input string, right? So now we can do one of two things. We can say, well, let's define the model to be one where you don't pay for S. Okay? So this is something that's called a random oracle model. So we say that randomness is free. There are random bits out there, and you can dip into this pool of random bits anytime you want. The space used to store these random bits don't really count towards your storage. That's not working memory. Okay, that's just a model definition. And if you're not satisfied with that, as many people shouldn't be, then you could say that let's rethink what this algorithm is doing and see if we can use randomness more efficiently. And indeed, we can in both of these cases. For L2 estimation, you can prove, and it comes out of the analysis, that the columns of that matrix I was showing you need only be 4-wise independent. They don't need to be fully independent. And this means that you can use some kind of a hash function and a short seed to generate the columns on the fly. Right? So now we have an algorithm where it's genuinely logarithmic space, including counting the random bits used by the algorithm. You can do something similar for L1 estimation, but the argument is a little more involved, and it goes through this construction of Nissan's space-bounded pseudorandom generator. Okay. So this then raised a question, or in my mind at least raises the question that, so in these cases, maybe we were lucky and we could convert our random oracle algorithms into sort of these more realistic, what I'll call random seed algorithms. So in a random seed algorithm, I'm paying for the space used by this random seed. Whereas in a random oracle algorithm, all randomness is free. So were we lucky with these problems, or is there a general theorem, right? So if there isn't a general theorem, can we show that there's a separation? So can we find a problem whose random oracle space complexity is much less than its random seed space complexity? Okay, and if you think about this for a little, you'll realize that actually no such separation is going to be possible for a somewhat annoying reason. You can use this theorem called, which communication complexity people will recognize as Newman's theorem. It says convert public coins to private coins. If you don't know what I was just talking about, this is a kind of existential result. It says that you can convert an algorithm of this type into an algorithm of that type. But the converted algorithm is no longer explicit. So it's like you cannot write down its pseudocode. So it's a bit unsatisfactory. So on the one hand, it shows that such a separation won't be possible to prove, but the kind of algorithm it gives you is non-constructive. Okay, but this was for classic streaming. When we look at adversarially robust streaming, the argument using Newman's theorem, which of course I haven't shown you, doesn't go through anymore. So there's hope that you can actually separate these models for adversarially robust streaming, and we indeed do. So that's kind of the upshot of this work, or I should say the culmination of a series of works. They all involve my student Manuel Stockel. Yeah, let me give you a little bit of a history of how we came here. This is not meant to be a history of adversarially robust streaming, which I think Samson did a great job of going over in the morning. This is kind of biased towards getting to the point that I'm trying to make here. Okay, so the field kind of started with this classic paper of Hart and Woodruff. They didn't use the term adversarially robust streaming, but they were thinking about whether you can attack linear sketches that try to estimate L2, and they showed that indeed you can. Right? And then the field really kicked off around 2020 with a series of very influential works involving some of you guys. And a lot of these works were focused on coming up with robustification techniques. So techniques for converting a normal streaming algorithm into one that would be robust. And we actually seen some of these already. Okay. Many good results are there, but maybe one thing worth mentioning is that if an adversary gives you items from some universe and you want to estimate the number of distinct items, this is something that can be done in logarithmic space in the classic streaming world, and can also be done. Ignored several factors that might influence the result, but it can be done basically in this robust setting as well. Okay, and now I have to Uri is here. Stock 21 was remote. We were all watching each other on computer screens, and I saw Uri give a talk on at Stock 21. I'm sure you remember this. It was part of a tutorial, and he mentioned this separation question, specifically in the context of adversarial robust streaming. And I have to thank Uri for this talk. Inspired me to think about this and really start working in the area. So okay, there was a separation that was, don't know if it was known at this point or came soon after, but there's a separation given for a kind of data analysis problem, which is arguably a little bit adversarial. It's set up to cause the separation. This is not a knock on the paper by any means. There's a lot more going on in the paper, but there was a separation known. But for various reasons, we thought that, okay, I can't explain this problem easily to somebody else. Okay, how about a problem that is natural and everybody knows what it is? And we went looking, and we eventually realized that graph coloring demonstrates this kind of a separation. So the best thing you can do with adversarial robustness and without adversarial robustness actually has a provable separation in space. And along the way, we realized that actually you don't even have to look at something as complicated as graph coloring. We can look at this very simple toy problem called missing item finding. I mean, it's a toy problem, but it's also natural. And I will define the problem in a bit. And that gives us this separation already. So then Manuel Stockel, he went about trying to understand in very great detail the complexity of this MIF problem. And in the study, during the study, he realized that exactly how you use randomness in your algorithm affects the space complexity. All right, so that's what started this present line of work, and it's now continued here. Right? So what are some of these forms of randomness? So let's look at least 4 kind of classic examples and see in what ways they use randomness. So for approximately counting, say, high frequency items, there's this classic algorithm of Misra and Greaves. It is a deterministic algorithm, therefore doesn't use any randomness at all. Probably one of the first streaming algorithms one teaches in a course. And then maybe the second or the third algorithm you teach would be count sketch or count min sketch. This is an example of a random seed algorithm. Okay? You start off with some kind of a hash function. That's what you choose as your randomness, and the rest of the processing is now deterministic. Then you have a bunch of algorithms that do sampling, like reservoir sampling or the Morris counter, a classic algorithm. These algorithms toss random coins at every step of processing input. Right? So they are using a lot of randomness. However, they're not storing all this randomness. Right? So they're still kind of not cheating by having this freely accessible pool of randomness. And finally, there's this thing there where I say, okay, fine, go ahead and cheat. You have a infinite pool of randomness and read it as you wish. This is what we call random oracle algorithms. And in general, a linear sketch might look like that.
So generally mean that you cannot generate the random.
Yeah, maybe there's no explicit way to generate the matrix entries again. Yeah. Of course, there will be a non-constructive way because of Newman's theorem, but yeah. All right. So Now, specifically the missing item finding problem, what is it? So we have two parameters, n and L. N is the size of the universe, L is the number of items that I'll give you in the stream, and it's going to be, think of it as considerably less than n. So it's at most n over 2. Often it will be sublinear in n even. And the goal, of course, is at each step you have to output an item that's missing so far. The output yi that's not in x1 to xi. We want the probability that over the entire course of the algorithm there is ever an error to be at most inverse polynomial, and maybe let's say 1 over n squared for concreteness sake. Okay, now before we worry about adversarial robustness at all, let's ask ourselves, what is the randomized space complexity of this problem, right? There's no adversary, so the worst case stream is written in advance. We just have to produce these missing items. Yeah. So a little bit of thought should convince you that this problem is not terribly hard. What you should do is choose a bunch of random elements in your universe in advance of seeing the stream and say, I will always produce outputs from this randomly chosen set. Okay, so now the stream comes along. If you're unlucky enough to hit one of these randomly chosen elements, you say, okay, cancel that. Don't give this as an output. Otherwise, just repeat something that's available in your pool. So it's not terribly hard to analyze this and realize that the space you need for this is log of 1 over whatever error probability you want. And so in this case, it's log n, or an inverse polynomial error. Okay, let's ask another interesting question. This algorithm is essentially randomized, I mean, crucially randomized. What about a deterministic algorithm? Then you may think, you probably can't do anything deterministically. You have to store the whole stream. Storing the whole stream will be order L space, or maybe actually L log n. But you'd be mistaken if you thought that you really need to store the whole stream, right? Okay, so there's a trivial reason why you'll be mistaken, which is that you don't actually need to store the elements in the stream. Maybe all you do is you say your pool from which you will produce outputs is the first L plus 1 elements in the universe. And all you do when the stream comes in is you have a bit mask and update it to say, have I seen this guy, have I seen this guy, and so on. So L plus 1 bits will suffice. They'll give you a correct output. Okay, is that a lower bound? So that isn't a lower bound. One can show, in fact, Manuel showed this, that you can get a bound which is L divided by some logarithmic term, log n to the base L, this kind of weird looking function, but it at least hints at something wizardry going on with the algorithms, right? So whenever there's algorithmic wizardry, and this is something kind of philosophical that I say from many years of experience, it means proving lower bounds is going to be hard. Okay, so algorithms can actually do something non-trivial, which means lower bounds have more work to do. Okay, all right. So with that background, let me now define the models of, or the types of randomness that we consider in this book. So one, of course, is deterministic. There's no randomness at all. Let's use the notation det n comma L to mean the space complexity of missing item finding with parameters n and L when the model is deterministic. Okay. So next up is pseudo-deterministic. So this is like the weakest kind of randomized algorithm. So you may use randomness, and now here's the definition. With high probability, you must give one particular answer sequence. So given a particular input, if you rerun the algorithm with fresh random bits, most likely you will see that same output all over again. Right? That's so there. From the point of view of somebody who's studying the outputs of the algorithm, it looks like the algorithm is deterministic. Right? With some small probability, of course, you may deviate into something arbitrary. All right, so next up is a random seed algorithm where you can toss and you have to store these random coins before you see the input. And then after this, the algorithm is deterministic. There's no further randomness. Next up is random tape, where you can repeatedly toss random coins. You don't have to toss them all in the beginning. And this is like sampling algorithms. We keep tossing random coins that fall into this model. But importantly, you never get to reuse, or you don't get to look at what random coins you previously tossed. And if you want to look at them, then you have to store them. And at this point, you'll pay for their cost. You'll pay your space cost. In the random oracle model, of course, you just have an infinite random string, infinitely long random string. It's available for free, so it doesn't count towards the space cost. Okay. So results, this is a summary of all the results. This is not all from this work, so some of it is from the first initial work by Manuel, and then some of it is from our joint work, which followed up on that. Yeah, I mean, I guess there's, I can throw a table of results like this at you. So in each case, there is a lower bound and an upper bound on the space complexity. I have all these models, right? So I have random oracle, random tape, random seed, pseudo deterministic, deterministic. So this is the more and more restrictive as you go down the table. So these are the most restrictive algorithms, therefore their complexity should be higher, as indeed it is. This is the sort of baseline, not adversarially robust algorithm. We just allow an arbitrary randomized algorithm here. This just for comparison. So pay attention to three specific separations. Okay, so there are three different exponential separations. So this one shows that the requirement of being adversarially robust increases your space complexity exponentially, at least for the right setting of L. If you take L equals n to the 2/3, this upper bound is logarithmic, this lower bound is polynomial. Then there's this one. This says that between random oracle and random tape, so if you keep getting to toss fresh random points, that actually is exponentially more powerful. So if you take the setting of L equals n to the 1/3, then this upper bound kind of goes away. It's just polylogarithmic. Whereas this lower bound is something polynomial now. And then finally, between random tape and random seeds, right. So random seed being the one where you toss all your random points at the beginning, and after that, it's all deterministic. So here if you set L to be something like 2 to the polylog, 2 to the root log n for concreteness, then this is small. It's basically this upper bound goes away, and the lower bound on the other hand is still polylogarithmic enough. Okay, so there's a separation here, but it's only quadratic, and there's essentially no separation here. There's some log factors that are being hidden, but still limitation. But there's no separation. Okay, there's a lot of things that I could talk about. I'm choosing to say a little bit about these two things. So they're both lower bounds. So I'll tell you a little something about the random oracle lower bound, and then a little something about the deterministic case. Admittedly, the most interesting bound is one of these. It's actually this thing, the most interesting bound. But it's also very hard to describe in a short talk. Okay. All right. So how would we go about proving this lower bound? We're going to make a communication complexity argument, but with a little bit of a twist. It can't be the usual sort of communication complexity argument, which would have given you a lower bound against just algorithms that need not be adversarially robust. So this argument has to use the fact that the algorithm is actually robust. So how's it going to use it? So we'll create a communication problem that looks like this. So an input X is going to be summarized with some kind of a sketch. And when Alice and Bob simulate this adversarially robust algorithm to produce a protocol, the protocol is going to do something like this. So Bob will continue the algorithm based on Alice's memory content. So far, that looks like the standard reduction from communication to streaming. But what Bob is going to do is not just to produce one answer and go away, which is what normally happens. But here he's going to produce an answer, basically exfiltrate some information about X, and then use the results to kind of continue the stream. And we know that the algorithm must continue to work well. That's what it means to be adversarially robust. And so then you can exfiltrate some more information and so on. So the net result is that Bob will try to extract a whole bunch of information about X in the form of some object Y. Okay, so let's make this a bit more concrete, specifically for the missing item finding problem. So here's a communication game which has that nature, and I will soon show you that this is really what you need for missing item finding. Alice is going to have an input set in some universe. Bob's goal is to produce a large output set that's disjoint from Alice's input set, so that avoids Alice's set. And we can show the following communication load bound. So any one-way protocol for this problem requires a message length of A times B over M. So product of the two set sizes divided by the universe size. Okay. Right. Okay. This result will now separate classic streaming from robust streaming, right? But it is not enough to separate the different gradations of robust streaming. Right? So this will basically apply against random oracle algorithms, the most powerful form of randomness. Okay. Yeah, okay. In the interest of time, I'll keep saying why I put that. So why does this imply a lower bound for MIF? So suppose you have a robust algorithm for MI, missing item finding. How do we get a communication protocol for avoid? Now, it's really straightforward. So Alice will take, say, the first L/2 elements, right? So L/2 elements that constitute first set, and make them the first L/2 elements per screen. And then Bob repeatedly says, give me a missing item, give me a missing item, etc. And then creates a whole big set that's disjoint from Alice's set. That's it. That's the end of the story. And then you plug parameters in and you get the bound of the story over. Okay, so that's all very well and good. But what if the algorithm was allowed only a weaker form of randomness? What if the algorithm was deterministic, right? Then can you prove a higher lower bound? I mean, I claim that you can prove a higher lower bound. How will you prove it? Now, you can't do it using this problem because this communication problem actually has a deterministic upper bound, right? So you have to do something else. And okay, so let's briefly talk about this. So to get a deterministic bound, we have to sort of rethink what this protocol is doing at a, not protocol, what the algorithm is doing at a very fundamental level. So let's visualize it as a branching program like this. So suppose our algorithm uses Z bits of space. So that means basically at any point of time, it's in one of two to the Z states. Okay. Draw the whole computation as this kind of branching program. So we read a stream input and we move to one of the state, right? That's what's going on. So for each state in this branching program, in some layer, there is going to be a set of possible outputs. What I mean is, from here on, if the algorithm had to report missing items, then there are all these various continuations of the stream. Along each such path, there will be a sequence of outputs produced. So let's collect all such outputs and call that set outs signal. So note that it's a function only of the state of the branching program, right? Now, any particular prefix of the input stream leads us to a specific state, which then gives us a specific set of outputs. Okay? So let's call that set f sub x. So f sub x is all the outputs that the algorithm may give upon reading the prefix x. They have to be disjoint from x by correctness, right? That's what it means to produce missing items. So now, there will in general be multiple inputs that collapse into the same state of your branching program. So if x and y are two such prefixes leading to the same state, then of course fx should be equal to fy because they're both functions of that state only. But then this correctness criterion tells me it must be disjoint from n minus x and from n minus y. Therefore, it must be disjoint from n minus x union y. And it's not just two unions, not just a union of two things. It could be multiple paths, and so you'd be doing a union of multiple things. So the further along I go in this branching programs, the more different things are being unioned together, and this set will start shrinking as you go along the branching program, right? So the intuition is that if z is too small, then fx will shrink rapidly and something bad will happen. Some contradiction will happen. Okay, so I'm saying that exactly one of the following two things will happen. It may be difficult to understand what is being said here, but if you look at it syntactically, you'll know that one of the following two things must happen, because this is the opposite of that. Right? Okay. Okay. So that's not too hard. All right, but now let's actually think about what's being said. So either there is a prefix such that for every length t continuation of that prefix, the output set does not shrink by too much. So I'll call this the non-shrinkage case, and the opposite is the shrinkage case. Okay, so in the non-shrinkage case, I claim that this gives me an avoid protocol that's too good to be true, right? So we're saying that if the universe is the set of all possible outputs from this point on, and then Alice has these inputs, then Bob will produce an output from that set, which is large enough, and therefore you get a too good to be true avoid protocol. So if you use the communication lower bound for avoid, that gives us a space lower bound of omega t, where t is this thing. So the question is, of course, what value of t can I use, right? Now this case, so if this case ever happens, then I'm good, I got a lower bound. So the opposite is that shrinkage happens all the time. So it means that no matter what prefix I have, there is going to be a continuation that causes this f set to shrink. Okay, so this means the f set shrinks by a factor of half each time, but this can't happen too often because it cannot shrink to less than 1. You always have to have a valid output. The f set cannot possibly shrink to less than 1. So this upper bounds how many times I can shrink, and that in turn tells me that t, so long as t is something smallish, then I have some kind of a contradiction. Because if t is too small, then I can, of course, add t more continuations. I can add several continuations of length t, and then something's wrong. Eventually, I have to have too many shrinkages. So that tells us eventually there must be a non-shrinkage step, which gives me the lower bound. Okay, so may have been a bit fast, but hopefully you got a bit of a flavor of the argument. Time-wise, I think I may be exactly on the cusp, right? Yeah, okay. So I deliberately did not write too much about the random tape bound. I won't even go through this bird's eye view. This is meant to represent that couple paper, right? So, okay. But I'm happy to tell you more about it if you want offline. Let me end with some open problems that, I mean, of course, there's lots of nice open problems we saw earlier in the day. But let me highlight a couple of things. Of course, we know this is already highlighted. So for estimating 2 norm, it would be nice to have really strong lower bounds for doing this. I think Omri's statement was that this is the most important problem in adversarial robustness, right? Yeah. Anyway. But yeah, in general, find more such separations between classic streaming and robust streaming for hopefully something a bit more practical than just missing item finding, which is a little bit of a toy problem, but illustrates all these things, all these principles nicely. And something else that I've been curious about, but I haven't managed to do anything with it, is this line of work seems to have some similarities, at least superficially, with the line of work on mirror games. If you don't know about, look up what this is. This is a little bit older than our work. And it'd be nice to see if techniques from this line of work can solve some of their open questions. Okay. All right. So with that, I'll stop. Thank you.
Questions? So you mentioned mirror games, but not card guessing games. So
Yeah, okay, that's true. Yeah, sure.
are they also related?
Yeah, I suppose so, in the sense that those are related to mirror games themselves, aren't they?
I think there's been some work by Monier also on.
Yes. I think one of Moninar's papers referred to Stokel's earlier paper, so he's at least aware. But I forget the exact model. So maybe his model corresponds to what would be called a white box adversary. Oh. Anyway, no, I could be mistaken.
That's several ones, but it seems some.
Oh, yeah.
So there's a log L factor difference in the deterministic upper and lower bound.
Correct. Yes, right. Yes, there is. The lower bound has a divide by log L, and the upper bound has a deterministic, right? Oh, sorry, no. What? Deterministic upper and lower bound.
Are they matching now, or?
They're not exactly matching, but I think it's like a really low order difference. No, the upper bound is already L over log L. The lower bound is I forget quantitatively what it is. I don't think it's like log squared. It's not even a 1 log L difference. But there's some gap.
And what's like the algorithm, like you said, right? It's some.
Oh, what is the algorithm that shaves the log factor?
Yeah, wizardry.
So I don't know how to say this without getting into all the details, but let me try. So remember the algorithm that I was saying about you maintain a bit vector for the first L plus 1 element, so you pre-decide. So suppose you do this a little bit coarsely, and you have one bit for every bucket of some width. And whenever your stream contains an element inside this bucket, you just set that bit, saying that this bucket is now potentially damaged. But when a bucket is damaged, you just don't eliminate it altogether. Now you maintain more detailed information about the inside of that bucket. So that's roughly what you do. And then you do several levels of this.
I had a question about the hierarchy. So it is a strict hierarchy, right? Like or some of the bounds like L squared plus
Okay, it depends on what you mean by strict. If you mean exponential separation, then there is no exponential separation here yet. And there isn't really a separation here.
Well, I guess I meant like is the L squared over n, is that actually L squared over n?
If this or that.
Sorry, the other way around. Like I guess the root L would be like L plus L squared over n.
Oh. You mean this upper bound?
Both upper bounds and lower bounds. Like, because one should maybe intuitively think that random orbitals are stronger than random seeds.
Yes, of course, yes. So this space complexity should be less than this, as indeed it. Oh, I see. So you're saying if the nature of these functions are such that. I'm bad at doing this in the head calculation, but is there a setup where you're saying that this function as written can possibly be less than that?
L equals n.
L equals n. So if I send L, yeah, I did say in the setup that L is at most n/2, say. So then this would be a 1. This would be okay. I see what you mean.
So they
I see what you mean.
it works.
Yeah. Sure. They are. Yes. Yeah, so you're saying this result should not just say root f. Presumably should have a term that's yeah. So if you set L very large, then you're saying this is giving something too good to be true in light of that. But okay, so then there are some caveats which I may not have mentioned, such as if for L in so and so range, this result is true, and so on. Or alternatively, you can do the plus business, as you said. Yeah, it's not. It's meant to be a table that's visually somewhat not off-putting. So, yeah, if you really write the full formal statement of the result, then the function is complicated.
Questions? All right, let's keep it again.